right, guys, so I think that the video is started. We're going to get started with doing actual calculations with Newton's second law. So before I get started, one thing I'm going to remind you guys is you want to have a color coding device, and you're also going to want to make sure you have a calculator ready because it is going to involve some computations. So our goal by the end of this lesson is to solve problems involving changes in motion by using Newton's second law. So Newton's second law is this relationship between three variables: net force, mass, and acceleration. Now, when objects are accelerating, that either means they're speeding up, slowing down, or changing direction. So when there is acceleration, that means there is a change in motion occurring. So there's all kinds of situations that involve changes in motion. We've got an image right here of a car experiencing air resistance. This could cause it to slow down when you stop pressing on the gas. We've got a scenario right here of someone in an elevator. When you're in an elevator and you go from being stationary to all of a sudden moving upwards, that involves an upwards acceleration. You're speeding up for a small moment. We've got someone right here who's experiencing traction. If we don't have traction between our shoes and the ground, we see that we don't accelerate forward and we aren't able to change our motion. We end up being stationary. This is why trying to walk on ice where there's very little traction can be so challenging and frustrating, because you can't really get that motion forward. And then we've got an image of a bridge right here, and this doesn't really involve a change in motion, but really a lack thereof. Bridges are designed to keep objects from accelerating, and that means that forces need to be balanced. And Newton's second law plays a role in making sure that forces are balanced and that we don't experience an acceleration regardless of the mass that we maybe put on a bridge. So we're going to get right into some problem solving by talking about what the heck is Newton's second law. So Newton's second law is really a relationship between these three variables that can be written as an equation. So you're going to hear me often say unbalanced force and net force interchangeably. I'm referring to the same thing. So the net force on a force diagram is the same thing as the unbalanced force. And what I mean by unbalanced is I'm talking about the part on a diagram that didn't get balanced out by anything else. Now, your net force is equal to your mass times your acceleration. The more common way, or I'm sorry, the less common way you might see this equation written is that your net force divided by your mass is your acceleration. Typically, when we're talking about what makes sense, we'll refer to this equation here on the right, because it's pretty easy to talk about how is acceleration affected by net force and how is acceleration affected by mass. And when we're doing that, we're really thinking about this equation here on the right. But as far as computations and solving mathematical problems, this equation here in the middle or on the left is going to be a little bit easier for solving math problems. So in words, what does Newton's second law mean? Net force, your unbalanced force, is directly proportional to your acceleration. You could write this using this notation. That notation I just wrote was me saying that net force is directly proportional to acceleration. What that means is that if net force increases, acceleration is going to increase by the same factor. So if I double net force, I'm going to double acceleration. And that makes sense. The more force I exert on something, it makes sense that it'll accelerate a little bit more. This also means that your net force is directly proportional to your mass. And here's how I think about this. If I increase the mass of my object. So I take, a baseball and a bowling ball, and I want to accelerate them at the same rate. So I want them to speed up at the same rate. The bowling ball, having a larger mass, is going to require a larger net force to get the same acceleration. So as I increase the mass of my object, I'm going to have to increase the net force that I apply to get it to accelerate. Since these are directly proportional, they increase by the same factor, and they also decrease by the same factor. Directly proportional just means that these two variables will change by the same factor. Now, mass is inversely proportional to acceleration. So we could write that using this notation, or we could just say that, as mass increases, acceleration is going to decrease. They change by what we call reciprocal factors. Reciprocal factors. So if I double my mass of my object, my acceleration, instead of increasing, it's going to decrease. It's going to get cut in half, because 1/2 is the reciprocal of doubling, or the reciprocal of 2. So let's look at some problems and use that relationship. So how will acceleration of a cart be affected when the force on it doubles and the mass on it triples? So when net force is doubled and mass is tripled, how is acceleration going to be affected? Well, I know that net force is directly proportional to acceleration, and I know that mass is inversely proportional to acceleration. So what this means is that acceleration is going to experience two changes. Since it's directly proportional to net force, I'm going to color code here. This means that it's going to change by the same factor. So if I double net force, I'm going to double acceleration. I'm going to change color coding devices. Since mass and acceleration are inversely proportional, this means they're going to change by reciprocal factors. So instead of tripling my acceleration, I'm going to be multiplying it by the reciprocal. And the reciprocal of 3 is 1/3. This is the equivalent of dividing by 3 as well. So if it makes more sense in your brain to say, okay, I'm going to take my acceleration, double it, and then I'm going to divide it by 3. Dividing by 3 is the same exact thing as multiplying by 1/3. So I'm just going to leave my answer like this for simplicity. So this is how my acceleration is going to be affected. It's going to be doubled, and then it's going to be cut into 1/3. So moving on to the next example, how will the force required to accelerate the car be affected if the mass doubles and the acceleration is halved? So now I've got my mass is doubling, and I know that mass is directly proportional to net force. The larger that something is, the more net force is required to accelerate that object. And if my acceleration is halved, I also know that acceleration is directly proportional to net force. So my net force is going to experience two changes. Since it is directly proportional to my mass, that means it's going to change by the same factor. So my net force is also going to be doubled. It's going to be multiplied by 2. And since my net force is also directly proportional to acceleration, that means it is also going to change by the same factor. So if acceleration was halved, that means net force is also going to be halved. So I could leave my answer as this, but as I'm looking at 2 times 1/2, I'm noticing that that goes away because 2 times 1/2 is the same thing as 1, because half of 2 is 1. So my net force actually is unaffected. It just stays the same because multiplying by 1 doesn't change the value of this number. So either answer is an acceptable way of explaining what's going to happen to net force. Now I'm going to have you guys pause the video for just a second and try the next one. When you're ready to check your answer, go ahead and unpause. All right, so if you're watching this, I'm assuming that you've unpaused, you're ready to go to check your answer. So for our last one, the try, how will the car's acceleration change if the mass triples and the force doubles? So my mass is being multiplied by 3, my net force is being multiplied by 2. I want to know what's going to happen to acceleration. So I know that mass is inversely proportional to acceleration, and I know that net force is directly proportional to acceleration. So acceleration is going to experience a couple different changes. Because it's inversely proportional to mass, I know that it's going to change by the reciprocal factor. So the reciprocal of 3 is 1/3. And since it is directly proportional to net force, that means it's going to change by the same factor. So since net force is doubled, acceleration will also be doubled. So this is how my acceleration will be affected. So let's move on now to problem solving using numbers that aren't as nice as doubling or tripling or halving our values, because sometimes we're changing by a very specific amount. So at the end of the giant drop free fall ride, riders experience a large upward normal force to bring their falling bodies to a stop. Determine the normal force value required to accelerate a 52.1 kilogram physics student with an upward acceleration of 27.4 meters per second per second. Wow, this is a lot of information. So the first thing that I'm going to do is I'm going to draw a force diagram for this person. So they're falling, and when they get to the ground, is it the ground that they're falling on? I suppose so. Yeah, they're falling to the ground, or I guess the ride that's holding them. When they're falling, they're experiencing a normal force. And this normal force is what's going to make them stop from their free fall. Now, since this person is on Earth, there's also going to be another force that they're experiencing. You might be able to guess. That force is going to be gravity. Now I'm drawing my force diagram unbalanced because this person is changing their motion, they're accelerating, which means that my forces are going to be unbalanced. My normal force is going to have to be larger than my force of gravity. And let me tell you why. My net force, my unbalanced force, I know is pointing upward. Why? Because they told me that my acceleration is upward, and acceleration and net force are always in the same direction. So if this person is accelerating upward, their net force they're experiencing is also upwards. So now that I've got a diagram, I'm going to start filling in some information. So I know that my acceleration is 50, oh no, not that, is 27.4 meters per second squared. That's another way of saying meters per second per second. I don't know what my net force is, but I can figure out my force of gravity using my person's mass, my student's mass. So if their mass is 52.1 kilograms, to find the force of gravity, I just multiply that by 10. So the force of gravity they're experiencing is 521 newtons. So this is a good chunk of information. The only thing that I haven't written down is that, you know, their mass is 52.1 kilograms, and that might be worth noting. So I'm just going to write that down over here. So now that I've got my thoughts organized, I'm going to start using Newton's second law to problem solve. So remember how I mentioned earlier that the equation that's easier to work with is this one right here. Excuse me. So this is the one that I'm going to use from the get-go. I'm going to plug in what I know and solve for what I don't know. I don't know my net force, but I do know my mass and I do know my acceleration. So I'm going to plug those in to my equation. So 52.1 kilograms is my mass, and then my acceleration is 27.4 meters per second squared. So if I want to know what my net force is, I just have to multiply these together. And here's where your calculator is going to come in handy. So when I multiply 52.1 times 27.4, I get a fairly large number. I get a net force of 1,427.54 newtons. Wow, that is a lot of net force. Here's what this number means. My net force is not the same thing as my normal force. My net force is that part that was unbalanced. Let me show you. I'm going to move this around right here. My net force is the length of this tiny little arrow that I've drawn. So it's not my entire normal force. It's just part of my normal force. My net force is the difference between my normal force and my gravity. So let me write out in an equation what I mean by that. My net force is the difference between my normal force and my gravity. And since my normal force is the larger force, that's the one that's subtracting the other force. So if I know my net force is 1,427.54, but I don't know my normal force, but I do know that my force of gravity is 521, I can solve for my normal force. So I'm going to do that by adding 521 to both sides. And in my calculator, adding 521 to my answer. And I end up getting a normal force of 1,948.54 newtons. This is my normal force. So now that I've got my answer, I'm going to box it because I'm good to go. That's all the question was asking for, was for me to find the normal force. So let's move on to another example. A hockey player accelerates a puck with a mass of 0.167 kilograms from rest to a velocity of 50 meters per second in 0.0121 seconds. Determine the acceleration of the puck and the force applied to the hockey stick to the puck. Neglect resistant forces. So there's a lot of information here. First of all, what I'm noticing is that they're giving me information about time and velocity. They didn't actually give me the acceleration of the hockey puck. So I need to know how to solve for acceleration. So throw back to Unit 3 when we were using kinematic equations. Your acceleration is how much your velocity changes in a certain amount of time. So for example, if I'm driving and I go from 10 miles per hour to 20 miles per hour to 30 miles per hour to 40 miles per hour, and I'm increasing my speed by 10 miles per hour every second, I could say that I'm accelerating 10 miles per hour per second, because that's how much my velocity is changing in a second. Every single second, I increase my velocity 10 miles per hour, 10 miles per hour, 10 miles per hour. So it's the same thing here. It's just instead in the problem, we're using meters per second instead of miles per hour. So our units are just meters per second. How much did your velocity change in this certain amount of time? So right away, I'm going to use my information about my velocity and my time to find my acceleration. So starting from rest and going to a velocity of 50 meters per second means that my velocity increased 50 meters per second. And the time that I did this in was 0.0121 seconds. So I need to plug this in my calculator and see what I get when I simplify this. And when I plug it in, I get a fairly large value actually. I get 4,132.2 meters per second. So that hockey puck is accelerating quite fast. But this is valuable information. So now I'm going to just draw a force diagram for the hockey puck. So I know that the hockey puck is on Earth, so it experiences a force of gravity. And I know that it's on the ice, so it experiences a normal force. Now, based off of my experiences with hockey, I don't believe that the hockey puck is accelerating into the ground or directly vertically, so I believe these forces are balanced. What I think is happening to make the hockey puck accelerate based off of what they've described with this hockey stick is that there's an unbalanced force pushing the hockey puck horizontally, maybe an applied force. Now, they told me specifically to neglect resistance forces. This means ignore air resistance and ignore friction. So I'm not going to put that on my diagram. I'm just going to include this applied force. Now, my applied force, since it's unbalanced, is going to tell me the direction that my acceleration is. Since my net force, or my unbalanced force, is pointing to the right, this means that my acceleration is pointing to the right, which I now know to be 4,132.2 meters per second squared. Now, I don't know what my net force was, but I can solve for that by using my second law equation, because I do know that my mass is 0.167 kilograms. So if I know my mass and I know my acceleration, I can find my net force. And based off of the diagram that I've drawn, my applied force is my net force because it's not being balanced out by anything else. So let's plug into our equation. My net force is going to be equivalent to 1.67 kilograms times 4,132.2 meters per second squared. So I'm going to plug these two numbers into my calculator, and I end up getting a net force of 690 newtons. Now, this net force is actually the same thing as my applied force from the hockey stick. So I've completely answered this question. I was asked for two things. I'm going to highlight my two answers in their respective colors. I was asked to determine the acceleration, which I did up here, and then I was asked to determine the force applied by the hockey stick, which I know is my net force right here. I suppose I could have highlighted that in blue now that I think about it, to stay consistent. So since I've completely answered both of these questions, I am good to go. So the next problem is a try. It's got two parts. I would say go ahead and try part A, pause the video, and when you're ready to check your answer, unpause. All right, if you're watching this, I'm assuming you've attempted part A, so let's get started. A basketball star exerts a force of 3,225 newtons, average value, upon the gym floor in order to accelerate his 76.5 kilogram body upward. Determine the acceleration of the player. So this one doesn't actually involve any math. It really involves your understanding of acceleration on Earth. So when you take a ball, let's just say, and you toss a ball up, it slows down and then it reaches a peak and then it speeds back up, right? That's because the ball is constantly accelerating towards the earth because there's a force of gravity constantly acting on the ball. And on Earth, it accelerates at a very specific value, 10 meters per second squared. Now, the actual value is like 9.81 meters per second squared. But for the sake of our class and for the sake of having easy math, we're just going to stick with the value 10 meters per second squared. So no math involved there. Just memory recall from last unit what the acceleration of gravity is on Earth. So now I would say go ahead and, oh, wait a minute. No, I did that whole thing wrong. I totally did that whole thing wrong. I am so sorry. Totally disregard everything I just said. I totally misunderstood the problem. Nothing what I said was false. Nothing what I said was false. When you release a ball and you let it go and it's in free fall, it absolutely does accelerate at 10 meters per second. I read the problem too fast and totally made a mistake. I'm so embarrassed right now. This is referring to the acceleration the basketball star experiences. I'm not the best at drawing, but I'm going to try my best. When they're jumping up off the ground. So this is talking about how they're accelerating themselves off of the ground. This isn't referring to them mid-air, which is what I misinterpreted as. So let me correct myself then and redo this. I'm so sorry if you panicked. So I'm going to draw a quick diagram here. I know that he has a mass of 76.5 kilograms. I don't know what his acceleration is. That's what I'm trying to find. But I know that he exerts a force of 3,225 newtons on the floor. That means that the floor is exerting an equal and opposite force on him. So the normal force he experiences is 3,225 newtons. Now, since he's on Earth, he's experiencing a force of gravity. And I can figure out that force of gravity by taking his mass and multiplying it by 10. So 76.5 times 10 is going to get me a force of gravity of 765 newtons. So now that I have a force diagram, I can figure out what my net force is. My net force is going to be the difference between normal and gravity. It's going to be that unbalanced part. So I have to subtract 3,225 minus 765. And when I plug that in my calculator, I end up getting a net force value of 2,460 newtons. So now that I have my net force and now that I have my mass, I can plug in to Newton's second law to solve for acceleration. Now, normally this equation would be best to solve, and you can absolutely use it to solve. Since we're solving for acceleration, what might be easier is using the second equation that I showed for you, because it's already solved for acceleration. Now, if you were doing this without me, and you just didn't even remember that that second equation existed, that's okay. You'll still get the problem correct using this equation. So I'm just going to show you to prove that that's true. So my net force is 2,460. My mass is 76.5. I have to solve for acceleration by undoing what's being done to it. So right now it's being multiplied. I undo multiplication with division. So I'm going to divide both sides by 76.5. So 2,460 divided by 76.5 gets me an answer of 32.2 meters per second squared. So this is my answer to letter A. Once again, I am so sorry that I spent that time explaining the incorrect answer. So take this opportunity to do letter B. When you're ready to check your answer, just go ahead and unpause the video. Okay, if you're watching this, I'm assuming you are ready to check your answer to letter B. So what we're going to do is we're going to determine the final speed of the player if the force endures for a time of 0.150 seconds. So they're saying, hey, he's spending 0.150 seconds pushing off of the ground. So he's spending that long accelerating himself off of the ground into the air. So I know my time and I know my acceleration. They want to know what my final velocity is going to be, or AKA, what is my change in velocity going to be? Because I know he's starting from rest. He's obviously not accelerating off of the ground or moving with a vertical speed when he first starts jumping off the ground. So I need to use my equation. Acceleration equals change in velocity over time. Once I know my change in velocity, I know what his speed is going to be when he's leaving the ground. So I'm going to substitute in what I know and solve for my unknown. So I know my acceleration and I know my time. So I need to solve for my acceleration by undoing what's being done to it. So right now it's being divided by 0.15. I'm going to undo that by multiplying by 0.15. Now, whatever I do to the right side, I have to do to the left side just to keep it equivalent. So 0.15 times 32.2 is going to get a change in velocity of 4.83 meters per second. So here's what this means. Whatever my starting velocity was, it increased, because this is a positive value, by 4.83 meters per second. Now, if he was already moving, I might have to do a little bit more thinking to figure out what's his final speed, but I know he wasn't already moving before he started jumping. So if he started from rest and he increases his speed by 4.83 meters per second, that means his final speed is going to be 4.83 meters per second. So hopefully you were able to get this. If not, I totally get it because it was your very first try. Practice is what makes perfect. So go ahead and move on to the independent practice.